Hello guys, welcome to another discussion video. In this video we're going to be looking at SDA alternative to practical paper. So this is 2022 paper, so we'll try to answer the questions and explain more of the lab practicals with chemical equations that help us to clarify what exactly is happening behind the scenes. Okay, also let's support the page, guys. We're trying to get to 1000 followers on the page, and let's keep liking those videos so that we can reach other students. Okay, all right. Also, just note that this videos is a full paper, so that means in papers like paper 3 the videos might be as long as 40 something minutes. Okay, so if you are, let's say, maybe lazy to go through the paper, you can just hold that ×2 button and then you just forward the video and then you can get to study. Okay, all right. So let's get through this paper and try to answer it all. Okay, so question 3 says, in an experiment to prepare sodium chloride, a student reacted sodium hydroxide and hydrochloric acid by titration method. The student transferred 25.0 cubic centimeter of sodium hydroxide into a conical flask using a pipette. A few drops of methyl orange indicator were added. The solution in the conical flask was titrated against the 0.0200 mole per cubic decimeter hydrochloric acid until endpoint was reached. The diagrams show the burette reading of the volumes of hydrochloric acid at the beginning and at the end of each titration. All right, so those are the burette readings, the initial one and then the final one side by side. So we have titration 1, 2 and 3. A Roman figure 1 says, use the diagrams to complete table 3.1. So we have table 3.1 there. We are to complete it. Okay, so let's just start here. Final burette reading. So remember, you're going to be taking this one because it's saying what? Final. Now that's something that some people can, omit. Okay, because the way your brain works is that it's trying to follow some sort of pattern. Okay, so you, from the titrations, you started with initial, you're ending with final, but for the recording you're starting with final and then recording the initial late, so which is kind of like you swap the positions with those. So that's something that some students might omit there. Okay, so let's quickly record the final. So the final here, so now you have 25 here, then 26 here. Now the way you take burette readings, it's kind of like the opposite to what a normal brain would think. Okay, so the readings increase downwards. Okay, the readings increase downwards. So this is 25, this is 26, so that means the readings are increasing downwards. And then to the degree of accuracy, now between 25 and 26 we have 10 digits. Okay, so that means we can record to a maximum of 0.0.9. okay, or the degree of accuracy is up to 0.0.1. so that means we can get 25.1 2 3 4 5 6 all the way to 9. Okay, which is very, very important when marking this paper. So the final reading there is 25.567, 25.7, and then the initial reading is 0.0. okay, remember 0.0, not just the 0. okay, remember our degree of accuracy is 0.1. okay, that's the degree of accuracy, so we need to show it throughout the readings. And then the volume of acid used, so we're going to say final burette reading minus the initial burette reading. So 25.7 cubic centimeter. The units are already here, so we don't need to put them this side. Okay, they are already included on the labeling here. Okay, so this is going to give us what? 25.7 25.7 cubic centimeters. Okay, 25.7 cubic centimeters. All right, so before we can tick any titration as the best, we need to first record all of them. Okay, then we can compare them side by side. Okay, then we can record them, we can compare them side by side. Okay, question 2 or titration 2. So the final one, remember, starting with the final, so it's going to be 29.8. Okay, 29.8. The initial, this one here, is going to be 3.4, and then the difference there, I already calculated it, is going to be 26.2. Then the final titrate, we have what? The final is 35 point. This is 5. 1, 2, 3, 4, 5. So 35.5, and then the initial one, this one is going to be at 10. So 10.0, and then the difference there is 25.5. And then now, to tick the best titration result, you compare the digits that you have, and then you find the ones that have a closer range. Okay, the ones that have a closer range. Now, in terms of closeness, you can see how you have 25 and a 25 point something, and then you have 26, which is a bit further from what we have there. Okay, so the 25s, the difference between 25.7 and 25.5 is 0.2. Okay, it's 0.2, whereas the difference between 25.5 and 26.2 is going to be up to 0.7 difference. Okay, so that's a big margin. This is why we're going to say the second titration reading is not really that accurate, so we're going to choose this one and that one, as they are closer in terms of deviation. Okay, they are not diverting, the numbers are not diverting away from each other that much. Okay, so let's continue. So we're done with our table. We can continue with the next question. Roman figure 2 says calculate the average volume of the acid using ticked values. So we're going to only take the ticked values. Okay, so our average volume is going to be equal to 25.7 plus, remember, average is the addition of the respective numerical values divided by how many of those numerical values do you have. Okay, over 2. So we punch that into the calculator, we get 25.6 cubic centimeters. 25.6 cubic cent. So this is one of the questions you should get free marks. Actually, this is just free marks. Okay, just free marks. Okay, let's continue. Roman figure 3, describe how average volume of acid can be used to prepare a neutral solution of sodium chloride. Okay, now remember, here I was just looking at the recordings, nothing else. Now let's dive deeper into the chemistry behind this reaction. Now we're saying we're reacting, let's go back to the question. We are reacting hydrochloric acid and sodium hydroxide. Okay, now remember that whenever you react acids and alkalis, okay, or an alkaline, NaOH, so this is an alkaline. Okay, it's an alkaline, and then so when you record this is going to be a neutralization reaction whereby the acid and the alkaline react to form a salt. Now the salt is going to have this metal ion and the negatively charged anion from the acid, so NaCl. Okay, because sodium ions are this, and then chloride ions are this, and then they can form this ionic compound. Now, of course, all group 1 salts are soluble, hence we can say aqueous there. And then the next thing you form is a neutralization reaction. You form a salt and water. H2O. H2O is a liquid at room temperature and pressure. I do believe the equation is balanced, okay? I do believe the equation is balanced, so we don't need to worry about that for now. HCl, aqueous. Okay, now there's another point that was mentioned here, okay? Now this happens until we reach what? Until we reach endpoint. What is endpoint? Endpoint is when all of the base or the alkaline has reacted with our acid and has been completely neutralized, okay? So at endpoint, the solution that you're getting is perfectly neutral, okay? It's neither acidic nor is it basic, okay? So that implies that we are only left with our salt and the water, okay? Our salt and the water. Now let's answer the question. Describe how the average volume of acid can be used to prepare neutral solution of sodium chloride. So you're going to react, okay? So you react this average, okay? You react this average volume of the acid HCl, of the acid with what volume of the base or the alkaline did we use? We used 25.0 cubic centimeters, okay? 25.0 cubic centimeters of sodium hydroxide, okay? Sodium hydroxide to form this, to form neutral sodium chloride, okay? To form sodium chloride. So basically here they want to check whether you understand what is happening in terms of the reaction itself, okay? They want to check, and then it's 1 mark. All right, let's continue. B says, describe how dry crystals of sodium chloride can be obtained from the salt solution. How can it be obtained from the salt solution? Now, the method of preparing salt here, we're going to use the evaporation method here, okay? So that's the general method that we're going to be using. Now, all we have to do is to list those steps that we're going to take, okay? So we're going to collect our salt, collect salt solution and transfer. Okay, we transfer it, transfer. So it's really important to mention some of the apparatus that we're going to be using into evaporating dish. Okay, evaporation dish. So you're going to collect the aqueous salt or the salt solution and transfer into the evaporating dish. Okay, now heat the aqueous salt or the salt solution to salt solution until saturation, okay, until saturation. Keyword here, saturation. Now whenever we prepare our salts, we don't want to heat them until all the water has evaporated. Why is that? Some of the salts might have low melting points, so they can begin to degrade. And also when you're preparing salts, you want those salts to have enough time for crystals to actually form from those salts, okay? For crystals to form from those salts. So we only heat our salt solutions until saturation, okay? So the last step is to allow for this saturated salt to cool, okay? So allow it to cool and crystallize, okay? Crystallize. So basically the last step here is allow for crystallization, okay? allow for the process of crystallization to take place. Are we together? Yeah, so that is going to be the the last step there. So 3 marks, 3 points. Let's continue. Now we're going to do a little bit of investigative chemistry. Okay, investigative chemistry. Question 4 says, Table 4.1 shows some tests, observations, and conclusions made when some tests are conducted on solid Z, which is a mixture of two salts with the same cation. What are cations? The way I tell my students to remember this is that there are some people who write T like this. Okay, so therefore cations can be written like this. Cations are what? Positively charged ions. So that is going to be what? All metal ions, as well as ammonium ion. Okay, ammonium ion. So that's one example of these are some of the examples of positively charged ions. So the way you remember it, remember, is through this T here. Okay, if you remember cations, obviously you know that now anions are what? Are the opposite of this. They are negatively charged ions, your non-metals. Okay, your non-metals. Okay, let's continue. A says solid Z is dissolved in water. Solid Z is dissolved in water. A solution is divided into 3 portions for test B, C, and D. A colorless solution is formed. A colorless solution is formed. Now, when you're forming a colorless solution, it means that whatever solid was, it has completely dissolved in the water. Okay, so therefore we can say our conclusion is that solid Z is soluble in water. Okay, solid Z is soluble in water. So that's the conclusion we draw from this observation. Okay, it's soluble in water. B says, to the first portion, aqueous sodium hydroxide is added and the mixture warmed gently. The gas produced is tested with. Now remember, you don't just look at this and then say start guessing. No, you even go to the other side and then you look at the information on the other side so that you get clues from that. Then on the other side it says ammonia gas was produced, indicating presence of ammonium ions. And then you go back to your chemistry. Which reaction gives us which reaction that involves ammonium ions gives us a gas? We know that there is only one reaction. The reaction between what? Between ammonium salts plus what? Plus a strong base. Okay, a strong base. So in this case, it's going to be sodium hydroxide. So in other words, what happened here was we had NH4. Remember, this solid Z is made up of, now we have confirmed it, it's made up, this cations is going to be ammonia. Okay, it's going to be an ammonium ion. All right, so we know that in this solid Z, it's a mixture of 2 salts, but they all start with ammonium. So it's ammonium something and ammonium another thing. So we can just say X, comma, Y. So those are the 2 negatively charged ions that are going to be part of this what? Part of these 2 salts. Okay, part of these 2 salts. Okay, so the gas here is going to be ammonia. The gas produced is tested with, so the gas produced is ammonia. How do we test for ammonia gas? We test it using a damp litmus a damp red litmus paper. Damp red litmus paper. Okay, why damp? you have to use a damp litmus paper because ammonia is a dry gas, so it can't really react with the litmus paper. So you need it to be absorbed into the litmus paper. Now, when ammonia gets absorbed into the litmus paper, into the damp litmus paper, the water reacts with the ammonia to form what? Ammonium hydroxide. And then we know that this is an alkali or a base. Okay, so since it's a base, it's going to turn a red litmus paper what? It's going to turn a red litmus paper blue. That's the chemistry behind the damp red litmus paper reacting with the ammonia gas. Okay. Okay, let me just erase this part and leave the our salt there. Okay, so that will use it as reference as we go along. Okay, so observation. What observations do we see when we are testing for that gas? What observation? So red litmus paper changes to or turns blue. Okay, so that's the observation. The damp red litmus paper changes color from red to blue. So that's the observation. Okay, let's continue to the second part. Dash is added. Dash is added. Then let's go to the other side to find clues. White precipitate formed, chloride ions present. How do we test for chloride ions? That's the question basically. To test for chloride ions, what we're going to use is that we're going to use acidified silver nitrate. Okay, so that's the test. You're going to be using acidified silver nitrate. Okay, so that's the test. Okay, that's the test. Acidified. So we're going to use, so what we acidify with is going to be nitric acid. Okay, so let me use the right pen. So we're going to add, okay, add acidified silver nitrate. Okay, so you're wondering, 2 marks. You get the 1 mark for the acidified part. You don't need to be specific that you are acidifying with dilute nitric acid, but you just need to keep that at the back of your mind. Okay, and then also we're going to be using what? Silver nitrate. Okay, silver nitrate. All right, so a white precipitate is formed, chloride ions are present. Therefore, remember the formula, the general formula of our two salts. It is NH4 and 2 unknown. Okay, the other one is going to be ammonium X, and then the other one is going to be ammonium Y. Now we have concluded that one of those negatively charged ions is going to be the chloride ions. So we are done with one of the salt. Okay, so one of the salt, let's just say Y, we are done with it. So that means we are left with what? NH4Y. We don't know this negatively charged ion. So we continue with the investigation. D Roman figure 1 says to the third portion, maybe let's just explain the chemistry behind C there. The chemistry behind C. Now when you add acidified silver nitrate, you get AgNO3 reacting with our unknown salt, okay, NH4X. All right, so in this reaction, what's going to happen is that you just get what? Double displacement reaction. So this is just going to be a double displacement reaction. So the silver takes this guy, the unknown negatively charged ion, plus ammonium nitrate. Okay, ammonium nitrate. All right, now a white precipitate is formed. Okay, a white precipitate is formed. and then it's concluded that it is chlorine. Okay, we know that silver chloride is insoluble. Okay, it's insoluble, hence we can get what? Hence we are getting this white precipitate. Okay, and then this guy, remember, all ammonium salts are soluble. All ammonium salts are soluble. Okay, so I'm throwing in a little bit of solubility rules as we go through this paper. Now, I just said all ammonium salts are soluble. That means this guy is going to be soluble. All nitrate salts are soluble. So this version of silver nitrate is going to be soluble as well. Okay. Okay, let's continue. D Roman figure 1 says, to the third portion, aqueous barium nitrate is added. Aqueous barium nitrate is added. And then let's look at the conclusion. It says sulfate ions SO4 2 minus or carbonate ions. Now these two, in terms of observation, they will give a white precipitate. Okay, white PPT, but you don't abbreviate. You as a student, you don't abbreviate. You write the full word, precipitate. Okay, white precipitate. Let me just remove this. Some of you might get the habit of abbreviating. White precipitate. Okay. Then Roman figure 2 says, then a few drops of nitric acid is added to the mixture from D Roman figure 1. The gas produced is tested with now carbon gas was gas produced. Now we're told the name of the gas. How do we test for carbon dioxide? We use lime water. Okay, we use lime water. What is the chemical formula for lime water? Is going to be calcium hydroxide. Okay, calcium hydroxide. So that's what lime water is. All right, now we have to do what? To talk about the observations. What observations are we going to draw here? We know that when you bubble carbon dioxide through lime water, it temporarily turns or gives a white PPT. Temporarily gives a white PPT. So we're trying to get the entire 2 marks. Okay, white PPT fades with continued test. Let me just use test. Okay, now when you continuously bubble the carbon dioxide through the lime water over a long period of time, the white precipitate will eventually fade away. Okay, the white precipitate will eventually fade away. Why is that the case? Now, in the first step where we get the white precipitate, okay, in the first step where we get the white precipitate, this is the reaction. Okay, calcium hydroxide is reacting with what? It's reacting with the carbon dioxide, okay, to give calcium carbonate. Now this carbonate is insoluble. Okay, this carbonate is insoluble, so therefore it comes out as what? As a precipitate, insoluble. So it gives us the white precipitate. So the other product is going to be H2O. Okay, the other product is going to be the H2O. Okay, now we continuously bubble the carbon dioxide through this lime water. Okay, so in the second phase of this reaction, what's going to happen is that the calcium carbonate plus the carbon dioxide with a little bit of this guy inside there will combine to form calcium hydrogen carbonate. Okay, calcium hydrogen carbonate, calcium hydrogen carbonate. So that is the product that is going to be formed. Let me just write this properly. So over a prolonged bubbling or with carbon dioxide through the lime water, you are forming calcium hydrogen carbonate. Okay, remember the two from the calcium will multiply this. Okay, now this guy is soluble. Okay, this guy is soluble, therefore that white precipitate disappears over time. Okay, the white precipitate disappears over time. Okay, so I'm just explaining this so that you can get the chemistry behind what's happening in that reaction there. All right, I think this is going to be our final answer question. Identify one of the salts contained in solid Z. So remember we said the base of, or the positively charged ion in all of the salts is going to be NH4 minus. Okay, and then we had X, Y, unknown negatively charged ions. The first one we confirmed to be Cl minus, then the other one confirmed to be a carbonate ion. Therefore, if you combine these as well as that, you get ammonium chloride. Okay, and then you get ammonium carbonate. 3. Now these two here, 2 minus, you put it to the other side, and then the plus, put it to the other side. Therefore, this is going to be NH4, 2 here, CO3. Okay, ammonium carbonate. So you can write either of these as the answer. Okay, NH4 or NH4 2 here, CO3. Okay. Yeah, I think that will be the end of this. So I hope you guys enjoy the revision. If you're interested in one-on-ones tutoring, please hit us on our WhatsApp. Don't forget to follow the page, guys. Okay, thank you.